All right, so if we're going to compare two samples, so let me, oops, back into the screen here. So if we have two samples of data, two collections of data coming across, I'm going to keep with the book's notation at this point. We have sample one and sample two. You'll see I sometimes revert to being X and Y because I like talking about the individual things in the sample sometimes. We're going to talk about their means. And so there's a collection of data in here, and I get the means. And there's a collection of data in here, and I get their mean. And what we can do is we can use what's called a two-sample z-test to focus on the difference of means. And so we can look at is the difference between sample one's mean and sample two's mean. And so here's what the conditions we need to use a two-sample z-test. Both the population standard deviation and the population standard deviation for both samples are known. Everything is random. Randomly picking through here. Of course, randomness is that test. We need things to be random for our statistics to work. These are independent. And the populations are normal, or n is greater than or equal to 30 for the first sample, 30, and n is greater than or equal to 30 for the second sample. So all these conditions that we've been carrying on for all of our different tests need to carry over here also. And what we're going to do is we make a new z-score. And that z testing score, I should say, right, is we take the two means from our samples, and we take the population means, and we're going to divide them by a special standard deviation of mean of the difference of means. So guess what? Standard deviation of the difference of means. And what this bit here looks like, so it's the standard deviation of the first sample divided by population, or the number of counts in the first sample, and the standard deviation of the second sample divided by the number of counts in the second sample. And the key is these are independent samples. And so let's look at one of these here. Let's see if I can get a good one here. So a credit card watch group. So remember, key, independent, and we know standard deviations. And something interesting is going to happen here when we do these. So, a credit card watch group claims there's a difference in the mean credit card debts of the households in California, and Florida. So we have California, and over here we have Florida, right? And so these things are separated, right? And so why I'm drawing the map of the state and across the country is these are really not independent things. And so what they're saying is the credit card debt in California is not equal to the average credit card debt in Florida per household. And so what they do is they take a sample. We go in and we survey some people here, and we get that the average credit card debt we find in California when we sample 250 people is $3,060. And the average credit card debt when we sample people in Florida, and we're going to get, we'll do 250 people also here, is $2,910. And other data from California says that the standard deviation in California is $960. The spread of the debt is about $960. And the standard deviation of Florida is $845. And so we have data and we have an idea of what is happening between the two states. So we can make a hypothesis, and the hypothesis is that these are not equal, right? That the difference, that there is a difference between the debt in Florida and California. Something about being over here makes you take different debt than being over here. And so we would make our null hypothesis that these are equal. Our alternative is that they're not equal. And our actual claim is going to be the null. And so this is a two-tailed test because we're looking at that type of alternative hypothesis. When we have a not equal, it makes a two-tailed test. And we're going to look for a significance level of 0.05. So at alpha of 0.05, our critical values are going to be z plus or minus 1.96. Those will be our critical values. And so what we do is we say z is equal to x1 bar minus x2 bar over square root of sigma 1 squared, the variance of 1 squared, over n1 plus the variance of 2 squared, or the variance of 2, over n2 squared. And if we scroll up here and grab our numbers, let's see here, 960 and 845. So let's do a little, we get 3,000, oh yep, and I forgot, we have mu1 minus mu2. I forget this in the equation, you're going to see why in a second. When we test a null hypothesis, we assume these are equal. And if they're equal, mu1 minus mu2 goes to 0. And this actually has an effect that we can use later on when designing an experiment. It's why you'll see me sometimes leave it out when I go to write it down. Over 960 squared divided by 250 plus 845 squared over 250. If I run to my calculator, I'm going to get 1.85. And so if I think of my standard normal distribution, and my critical values were at negative 1.96, 1.96. This test value is not in the rejection region, right? These are our rejection regions here. And so we fail to reject the null hypothesis. And so we can't say that there's a difference, or there is not enough evidence to say there is a difference between the credit card values, credit card spending in Florida and California. And so this is how we use or test for independent samples. So we get this expanded version of the z-test, where we have this special version of the denominator that has the two parts in it. Right? And so, but remember, this is independent. Right? Florida and California are separated so much that each piece of data here is relatively independent of the piece of data here. And we could talk something about how they're part of the same country. All right, let's do one more, and I'm going to flip over in the next video, and I'm going to do one more using the TI-84.